Hello, everybody. Welcome to the Munro Live Podcast. Munro is an engineering consulting firm with a design-first approach. We do benchmarking, teardown, costing, and design optimization. Here today on the podcast, I have Raimund. He's the VP of Business Development for Factorial Energy. And Raimund, before we begin, can you introduce yourself and tell us a little bit about what you do for the company and what you've done before you started working for this particular company?
Yeah, sure, John. Pleasure to be here. So my background is in chemistry. I've spent all my career working on solid-state batteries and commercializing them. So we're talking about Factorial Energy. We're a battery technology company based out of Boston, Massachusetts. So we develop next-generation technologies, particularly in the battery field, for all kinds of mobility applications. I do lead the commercial function, and this also covers the application engineering. So working closely with our customers, understanding their requirements, helping them integrate our technology into their vehicle and application.
So you truly are on a leading edge with a solid state. You're listening to the voice of the customer. There's a lot of customer demand for a solid state for various reasons. We're going to get into that today with this podcast. We're going to charge through this based on 5 different categories. So first, we're going to talk about technology and innovation, followed by commercialization and scale up. And from there, we'll talk a little bit about automotive partnerships and market strategy. You've got a lot of good stuff happening there too as well. The 4th topic will be performance and use cases. And the 5th and last topic will be, before we wrap, the future outlook and vision of Factorial Energy. So, sound good with you, Raimund?
That was great.
Okay, awesome. Let's rock and roll. So the first section is technology and innovation. I'm just going to read these off, and you've had a chance to look at these too as well. Can you explain how Factorial's FES quasi-solid state and Solstice fully solid state platforms differ in chemistry, performance, and target applications?
Yeah, sure. If we maybe take a step back and explain solid-state batteries in general, is about replacing the electrolyte in the battery. So you have the 2 electrodes. In the middle, there's typically a liquid in today's conventional lithium-ion batteries. And we're replacing this in twofold. So for FEST, we're replacing this with a quasi-solid-state electrolyte. So it's based on a polymer, our proprietary technology that we integrate in the battery cell. So this is, you could say, halfway there to all solid-state batteries. So it's what we consider quasi-solid. It still has a lot of the manufacturing synergies with today's manufacturing lines for lithium-ion battery. When we go to Solstice, this then is all solid state. So there's 0 liquid inside, and we're replacing the organic liquid with a ceramic. So the ions are conducting through the solid. And this is really the ultimate goal for this technology, to be fully solid. And this is where we also see the biggest jump in energy density.
Okay, good. Now, the Gamatron ML platform sounds like a game changer. At least it does to me. How does it predict cycle life from just 10 to 15 cycles? And what development time saving are you seeing by doing this?
Yeah, so Gamatron is our digital twin platform, and it's something we've developed organically from years of research. So the idea is we have all this access to historic data, to R&D data, and we combine this together with AI in order to accelerate our own process. So we can not only predict cycle life, but we can predict performance of certain compositions of electrolytes, of cathode and anode. And this really allows us to do smarter experiments. So we don't have to do all the types of combinations that you would typically do. At the same time, if you're able to predict if your cell will last 500, 600, 1,000 cycles, you don't have to wait all that long. So a typical cycle could take up to a couple of hours, maybe a day. And by this, we can cut down our development timing by multiple months.
So it's like a predictive future analysis of overall cell performance, looking at performance, reliability, and safety as well, right?
Yes.
Okay, well, that's nice. So this is a good one. What were the key scientific or engineering breakthroughs that enabled you to scale up to a 100 amp hour cell and achieve, this is a big one, UN 38.3 certification?
Yes. So for UN 38.3, you have to pass a variety of tests.
I think there's like 9, isn't there?
Yeah, there's a lot of testing. So first of all, you need to show a couple of cycles that your cell is actually functional. I think that's an important one. But then you also need to do some safety testing, so vibration testing and so on. And those tests they're pretty easy if you have an established technology. But if you have a new technology that has exceptionally high energy density, you need to show that you have high safety of the system. And we're able to pass this for a 100 amp hour cell, actually by now multiple times for multiple generations. And that was a big achievement for us.
And for those of you in the listening audience that don't know, UL is a third-party testing house. They perform all these different types of tests, so it has to be validated before it can go to market. I remember, I've been in battery for a long time, a few decades, and I remember solid-state discussion coming out, maybe more than 20 years ago, but then one of the big hurdles were dendrite formation. So a lot of companies, including you, have had to deal with this. So when we look at the dendrite formation and interface stability, our challenges with lithium metal and solid electrolytes, how does your technology manage or mitigate these issues?
Yeah, so the use of lithium metal comes with a couple of challenges. The key point for us is really the electrolyte. So we have to make sure that when we plate and when we strip lithium, when you shuttle the lithium ions back and forth in the system, that they plate homogeneously. And you can only achieve this when you engineer your interfaces. So if you combine a lithium metal anode with today's electrolyte, you would not get to a long cycle life, and it would be a very unsafe system. However, if you design the electrolyte, you make sure that there's good ionic conductivity, there's low interface resistance. This is how you can really achieve a homogeneous plating of your ions at the anode.
Do you work with a third party to develop your electrolyte, or is that done all in-house?
The electrolyte is done all in-house, so this is our own development. We were always careful to use commercial components, so we didn't want to have something so special that no one can manufacture it. And if you want to get to scale quickly, you want to make sure that you have a good supply chain network. But the electrolyte itself is our development.
That's good. That's basically the secret sauce of how things work within the battery. I know a lot of the companies out there, they develop their own or with a third-party electrolyte, and it's proprietary. It's kept under wraps, lock and key, and really nobody knows what it is.
It is different for different technologies, I would say. So right now we've become a technology company, so we have products where we source the electrolytes from suppliers. But the original, the FEST that you see all over the news, the 100 amp hour cell, this is truly our development.
So typically companies, as they progress through the manufacturing cycles, they go to scalability. We're looking at R&D, pre-production equipment. You mentioned you're in the pilot phase, which is just ahead of regular manufacturing, full scalability. How do you? Okay, so when you look at your process, how do you approach integration with existing lithium-ion manufacturing infrastructure to ease scalability? You have your own plant, but obviously maybe you want to sell your technology to an existing battery factory or company that wants to produce your product. They have a line already they have a line installed, and they don't want to upset too much of what goes on there. How do you integrate your product into a standard lithium-ion facility?
Yeah, John, that's a absolutely critical point, because there's a lot of capital that is bound in those factories, and quite substantial capital. So for us, for the first technology for FEST, it really targets to blend in with the lithium-ion battery manufacturing process. And the way we achieved this is that we bought most of the equipment off the shelf and then tried to run our technology. So that was by design a technology that can leverage existing manufacturing footprint. There is, of course, a portion, let's say 20 to 10% of this technology that needs adaptation. So we're doing something new on the anode. We use lithium metal. This is nothing that is present in today's gigafactories. But I think the majority of the process is really very much translatable to what we are doing. And that's also why we were able to reach that scale so quickly. So if you look around, there's not many technologies that made it this far to such a big format and the quantities we deliver today.
Okay. What is the capacity of your plant in Massachusetts that you could take it to full scale?
So currently, I'd say the design of our facility is really to serve this B sample qualification. So when you start in a lab, you produce very small samples, right? And reproducibility is not great. So this is something where you can call it an A sample maybe, or pre-A. But then the next stage is really to show, can you manufacture it repeatedly? Can you produce components where each looks the same? And it's kind of like the step before you go on a gigascale. Because when you go to gigascale, you don't have a lot of trial and error, right? It will just be immensely expensive to do such pilot runs.
Absolutely. And you're applying all the quality metrics along the way from start to finish to make sure that the product is uniform.
Yes, absolutely. That's required by our OEM partners.
Yeah, because producing cells is not an easy thing to do. It's extremely complicated to do. So I'm going to ask this question. We've already addressed it, but we're going to perhaps address it again. What are the most significant hurdles in moving from pilot scale to mass production, and how are you guys addressing them?
Yeah, that's the interesting question. So I think there's multiple things to it. For the first technology, we could leverage a lot of talent. So that made our life certainly easier. So if the process is more or less similar, you can use existing talent. You don't have to reinvent the wheel for everything. The other portion of it, I would say, is the supply chain. So you'd always have to work very closely with your partners that deliver the components to you, that they can match the same scale. So if you want to go as fast, you need to make sure that everyone kind of like tags along. And for some of the components that we use, this wasn't clear from the beginning. So today we're producing thousands of cells, but in the very beginning, I think we also struggled to find partners that could deliver in the quantities and also quality, as you mentioned, that we needed at this scale. So I would say that was one of the biggest challenges for us at the time.
Okay, so you mentioned partners. Let's jump into the third section of this particular podcast with you, Raimund. We're looking at automotive partnerships and market strategy. You're heavily involved in this, I know, based on your title and what you've said you do for the company. Your work with Mercedes, Stellantis, and Hyundai/Kia is notable. What have those partnerships enabled in terms of real-world validation and co-development?
Yeah, that's a great point. I think so. The battery development is very complex, but getting it in a vehicle adds even another layer of complexity. You need to understand what kind of tests you need to run, what kind of integration you need to perform. So we work very closely with those OEM partners to understand how we can integrate this technology in the vehicle. And to your point of real life validation, we just this week actually we had a modified EQS from Mercedes-Benz running from Stuttgart to Malmö. So that was a demonstration that Mercedes team has performed, and they have taken a big challenge to integrate our cells into an actual vehicle. So this allows us also to get data access to real life drive cycle data, and this is data that no one else is able to collect. So it's really important to us to see how does our cell perform in real life, and because in the lab the conditions are always ideal, right? You can select the temperature, you can select the sunshine and the rain, but in real life it's much different. You have a lot of other factors, vibration, very unique driving profiles, and that's something that our partners enable us to to look into.
Absolutely. Yeah, you have a good test platform outside the lab then with these guys. You mentioned a demonstrated EV with Mercedes achieving about 25% range improvement. Can you share more details about the vehicle specs and testing scenarios? Obviously done outside.
Yeah, absolutely. I think since of this week, we can actually talk about the actual range. So the drive that the Mercedes team has conducted is based on a single charge, and they achieved about 1,205 kilometers of range with a single charge. So that translates, let's just 750 miles roughly. And there was still range left, so they had about 130 kilometers of range left when they arrived, which is phenomenal. So this is it's a huge validation for us. I think a huge validation for the Mercedes team as well. And
Is this going to be posted on your website in the news section?
it's already public. As of this week, yeah, it's been published by Mercedes-Benz. So if you look on their website, you can find the press release. They released it.
That's good news. I mean, a range of over 700 miles on a single charge. That's crazy, unbelievable. It's good job. Yeah, you're welcome. Hey, what timeline do you anticipate before solid state cells reach production EVs? And are you targeting a specific vehicle segment, mid-range or luxury?
I would say, let me answer the second question first. I think naturally, initially, when numbers are low, you'll have to deal with increased pricing or increased cost rather. So that's why I would think that the entry point will be in the premium segment. Of course, the ambition is to really serve the mass market and pretty much replace lithium-ion batteries as the incumbent technology. In terms of timing, some of our partners have communicated already that they want to roll out this technology before 2030. That's a very ambitious timeline, but we're doing our best really to fulfill this. And I think if you take a step back and look at where we are with our B sample, I think you can imagine that this timeline is feasible.
Yeah, we've talked about the B sample throughout this podcast thus far. Can you explain what that is to the listening audience in case they don't know what it means?
Yes, so of course. So in battery development, you have to pass certain gates of development. So you run from A to sometimes D or sometimes C sample. So you have 3 or respectively 4 stages. In those stages, you increase first the maturity of the product. So A sample can be seen as the initial testing. Some of the design is not yet fixed. Maybe it's not even the target format. And then in B sample, you start freezing some of the design elements. So sometimes the chemistry is already frozen, sometimes just the design footprint is frozen. And this kind of ensures that you're very certain of what will you produce in the future. And then when you go to C and D sample, this is really where you have to show that you can manufacture at speed. So the pilot line is typically able to serve B sample, sometimes C if it's like a small volume. But you increase the maturity and also the number of samples that are being tested as you go through those sample gates.
Thank you for that explanation. So various stage gates, very important from A to some letter beyond A. You got to run through the gamut. Absolutely. Okay, so section 4 of this podcast, we're going to look at performance and use cases. You've cited an energy density of near 390 watt hours per kilogram for your first B sample, and you just told the audience what the B sample means. How does that compare to industry benchmarks today, and what's next?
Yeah, so the 390 watt hours per kg is exceptionally high. So that means you have a lot of energy for very little weight. If you compare this to today's lithium-ion batteries, you're probably looking somewhere between 250 and 300 watt hours per kg. So that's depending on where you jump off of, like a 30, 40, sometimes 50% increase in energy density. And that's quite substantial. You can see from also the driving demonstration that you get significantly more range in the vehicle. So I think that's the biggest value proposition for solid-state batteries. Lithium-ion batteries are, of course, catching up. So you can build energy-dense batteries at about 300 watt-hours per kg, maybe a little bit higher. However, you always have to consider safety. And this is where we go back to the all-solid-state, the solid-state electrolyte. This adds another layer of safety, so it actually allows you to build such high energy density cells and operate them safely.
So you get more energy in a smaller package. In any vehicle, could be economy, it could be a luxury. You're going to target luxuries going forward as you scale up. They're a lot safer, a lot better thermal management within the cell itself. Okay, so if we look at solid-state batteries, they're often associated with improved safety, as we just mentioned. Can you explain how FEST or Solstice improves safety, especially in thermal runaway or in abuse conditions? Because these are big ones.
Yeah, so this is one of the biggest pain points of the industry, is to make sure that you ramp up energy density, but you don't forget about the cell safety. And thermal propagation, maybe just for the viewers, is when you have one cell going into a thermal event. You want to avoid this cascade of events where all cells explode or burn because of a single failure in your battery pack. So the way our technology addresses this is by increasing the thermal tolerance of the cell. So if we take Solstice, for example, the electrolyte has a stability of about 200 degrees Celsius. So that's actually far, far higher compared to today's liquid electrolytes. So the liquid electrolytes, typically very volatile organic components, you should not exceed probably like 60, 70 degrees for those electrolytes, because you run into the danger that you develop gas, flammable gas, and this is where things get a little spicy. So I think this is where we really push the limit. So one thing to consider, of course, is the electrolyte is not the only component in the cell. So while we increase the safety of the electrolyte, you have some other components that will, from then on, limit how far you can push a cell in sort of safety. But increasing this thermal tolerance, even if a couple degrees, is a huge gain, because you can shrink some of the safety measures in your pack. You can allow higher operating temperatures. That's important for fast charging. That's important for racing. So there's a couple of benefits that we can leverage, not only in safety but also in performance with higher thermal tolerance.
So thermal runaway, for those in the audience that probably aren't familiar with it, and you did a good job explaining it, Raimund, is on 4th of July, you buy this string of firecrackers. You light the first firecracker, and then boom, 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 they all cascade. They work, they feed off of each other. So that's what thermal runaway is, like, for example, in a battery pack in a vehicle. So while we're still on the topic of performance and use cases, Raimund, are there particular applications beyond automotive that you see your product working in? Where do you see the strongest opportunities?
Yeah, totally. So I think if you think about what we do, is we decrease the weight, we decrease the space. So technically, this is relevant for any application, especially in mobility. So mobility applications are always looking for ways to either use less battery or to pack more energy to increase payload range. One area that we have explored recently is the drone market. So that's, of course, a market that came strategically very relevant all over the world. And we've shipped our technology to a North American drone company. And if you think about what a drone does, is it's like a vehicle that lifts off the ground, right? You have this vertical start and land. So you need a very high power and a very light weight. And that's something our technology can enable. And, this is, I would say, where I see the biggest synergy is short term.
Yeah, drones are part of the future, big time. They are right now, actually. So the fifth and last segment, future outlook and vision. Looks like you have a pretty bright future ahead of you. Gamatron predicts cell longevity early on. What are your current best figures for cycle life? Is it somewhere between 300 plus cycles, or is it already happening? 3,000, sorry, 3,000.
Yeah, we've already have cycle cells that achieve 3,000 cycles. Those are cells that are running in our R&D.
At 1C?
So,
Yeah, 1C.
this is C03. So that's typical automotive validation. So if you take drive cycle profile WLTP, for example, the average is roughly C03. So 3-hour charge, 3-hour discharge. And those cells, they actually take a long time to achieve 3,000 cycles. So you spend a year or two just waiting for this one result. So that's why those cells that have actually surpassed this very long cycle life, they're very small. And we're of course repeating this with the next generation, with the upscale generation right now. But that's also where Gamatron comes into play. Where we felt we don't want to sit around and wait. We want to know pretty much as soon as we start cycling, is this a good cell? Is this a bad cell? Is this something that has a future? Instead of waiting months and not moving forward.
Yeah, I remember in the battery world walking into the laboratory where maybe some of my buddies used to work, and it seemed like they're pretty boring work because they would stand there in front of cyclers, and sometimes the product, lithium-ion product, would be on their machines for, like you say, well, 6 months, a year and a half. It's like, really? Okay, well, that seems boring, but it's extremely important to do. Where do you see your company position maybe 10 years from now?
So I think, as we already alluded to, the technology we're developing is not only useful to automotive. I think we can imagine a lot of other applications in the mobility space, but also in the energy storage space, taking advantage of both a higher volumetric energy density and also a higher safety. I would say, looking forward, we will leverage a global manufacturing network. So our approach is to really partner with existing partners, existing cell manufacturers, and roll out this technology to all of those markets. So in 10 years from now, I think there's tremendous potential for solid-state batteries in all types of applications.
So we're talking in terms of future outlook, factories that are producing this product in gigawatt terms, right?
Yes.
Okay. That's a lot of battery cells in gigawatt. So cost, I think perhaps one of my last questions. Solid state is a little more money, of course, because we're not at scale with them yet than traditional or legacy lithium ion. How do you foresee the cost trajectory for solid state versus conventional lithium ion going forward?
Yeah, so I think as we mentioned, the determining factor for this is really achieving scale. So if we look at what will happen if we achieve scale for the electrolyte components for the manufacturing, so we're not at 1 gigawatt hour, but we're like 40, or like hundreds of gigawatt hours globally. The ambition has to be cheaper than lithium-ion batteries, because it's all a trade-off, right? No one in the industry wants a technology that is not able to surpass the existing. It has to be cheaper long term. I think in the meantime, we'll have to gain an advantage by achieving higher performance. So there will be certain applications in premium segments, in high performance segments, that are able to really make use of this additional performance. But then afterwards, I think the goal is to really lower the cost all the way to at least lithium-ion batteries, and even further.
So eventually, at the end of the day, your hope is to produce battery cells to sell to clients for them to either take them directly into the pack or into the module, and module into the pack. Are you guys also thinking about perhaps designing your own modules or your own battery packs going forward?
As of today, we have some projects where we, I would say we help customers integrate the technology, because the integration is different in some cases. So some of our technologies require some additional elements in the pack or just different elements than today's packs that are designed for lithium-ion batteries. Um, we're not necessarily a pack manufacturer, so I think we will have to see what the future brings. I think also from what kind of market segments we're entering. I wouldn't limit it to automotive. So this automotive packs are very complex, and we're very thankful for our partners to manage this type of integration. But for other applications, for drones, for power tools, it's much less complex. So that's something I could imagine us doing in the future.
What do you think your major competition will be going forward? You're trying to displace traditional lithium-ion to some degree. You have sodium-ion, you have LFP. You've got a landscape of different chemistries that you're going to eventually compete against. How you see yourselves working to achieve that?
I don't think we're competing with sodium-ion at this point, just because it's a very different segment. I think LFP certainly has become the benchmark in automotive, but also for a limited amount. So it's currently covering mostly the entry-level segment, going a little bit higher, but there's, of course, a finite limit of what this technology can achieve in terms of energy density, in terms of also the thermal stability. So we think there will still be a big piece of the market that will need chemistries like NMC, and that's our target market. So, and I think also solid-state batteries are not what we just mentioned is mostly the cathode or anode chemistry. This doesn't tell you much about the electrolyte. So there could be a future where you imagine a solid-state LFP battery or a solid-state sodium-ion battery. So we're not restricted to this one chemistry. It's more like a next generation, a new platform that replaces the electrolyte, but not so much the anode.
Well said. So, Raymond, as we wrap up this particular podcast, do me a favor and summarize what Factorial Energy is, what you're all about, and where you're going to position yourselves going forward. This is going to encapsulate everything we just talked about in a little package for everybody here at the end.
Yeah, of course. So Factorial Energy, we're developing next generation battery technology for mobility applications, for consumer defense, all kinds of different markets. And we're focusing on solid state batteries. So replacing the electrolyte in existing battery systems and enabling higher energy density anodes.
Okay. Thank you very much. Is there anything else you'd like to add, Raymond, before we wrap?
Not really. This was a very pleasant conversation. Thank you so much, John, for taking the time, and pleasure to be here.
You're very welcome. Everybody out there, thank you for listening to Munro Live Podcast. We have had the pleasure of speaking today with Raymond from Factorial Energy. And one day in the future, sir, I think I would like to go up to Massachusetts and see your facility there, and maybe we do a video shoot right on site.
Yes, we'd love to host you.
Okay.
Certainly facilitate that.
All right. Thank you very much.